In this video, we're going to talk about surface areas, calculating surface areas using double integrals. And we're going to look at two ways to do this. One is using Cartesian or rectangular coordinates. Or often called Cartesian coordinates. And suppose we have a surface given as, say, z is a function of x and y. So suppose we have a surface given in this way. Then the surface area is given by, you can call it A or area. Some books call it A with the S in parentheses, is going to be the double integral over the domain with a square root of 1 plus dz dx squared plus dz dy squared dA. So the partial derivative of z with respect to x, that's squared. Partial derivative with respect to y, that's squared, all under the square root dA, where d is the domain. And in this case, usually, or at least very often, this domain will be the domain in the xy axis, the xy plane, over which you want to find the area. So you want to find the area, so over, say, this domain in the xy plane. Another way we're going to do this is to find the area using parametric equations. Suppose we have a surface given as RUV is a function. So let's say we have some x coordinate UV, y coordinate UV, z coordinate UV, like this, basically just saying that this component will be in terms of u and v, this in terms of u and v, this in terms of u and v. So this is going to be a parametric representation of our surface. And then if you have this, recall that RU, R sub u, is going to be the derivative of this with respect to u. So you could think of taking the derivative of this, d du of r, and then v is going to be dr dv, the derivative of this with respect to v, then the area, the surface area, is given by this. RU cross V, absolute value, dA over the domain. Again, where D is the domain. So in this video, we're going to look at these two ways of calculating surface areas. So we'll begin using surface areas in rectangular coordinates. So we're going to start with rectangular coordinates. So let's take a look at an example, or actually we'll look at a couple of examples. And so let's take a look at this. Find the area of the part of the plane (3x plus 2y plus z equal 18), the part of this plane in the first octant. First of all, it's usually good to plot this, get an idea what we have, especially when we're told what the area of the part of the plane, and this really should say surface area. We want the surface area of the part of the plane of this in the first octant. So let's plot this. And if you recall, we can plot this very easily by setting, let's say if we want to find x, set y and z equal to 0. So if we set y and z equal to 0, make that 0, then 3x is 18. That'll give us 6 for the x. And then, so we can plot 6 over here. And then set maybe x and z equal to 0. And then solve for y. And that'll be 2y is 18, gives us 9. And then if we set x and y equal to 0, z will be 18. Something like this. So we can plot something like that. And of course, we're going to be integrating over this region in the XY plane. And so it might be helpful to plot that. So if we plot that on the XY plane, we'll get something that looks like that. And so let's go ahead and use our equation that we're going to use. We're going to use this equation over here. And so we're going to need to solve for z. So go up here, and z is equal to 18 minus 3x minus 2y. Then we're going to need dz dx, which is going to be minus 3. dz dy is going to be minus 2. And then we're going to, so our area. And let me just write out the equation we're using just to have it here. 1 plus dz dx squared plus dz dy squared dA over our domain. And let's put our numbers in. And let's see what we have. This is going to be 3 squared, which is 9. Plus 1 is 10. 14 square root of 14. Now, when you get to this point here, again, we could integrate, do the double integral over this region here, because remember, this is our domain D. And we could do the double integral as usual. But remember that if you get to this point here, we just have double integral D, where this is the domain. That's just going to be the area of the domain. And so, again, you could do it the normal way, but since we know that, again, if this is just a 1 here, you're able to factor everything out. Of course, you could not do this if you had variables in here. Of course, you couldn't factor them out. But here we didn't. This just came out to be a number. The square root of 14, we're able to factor that out. And so we really have 1 here. So this is the area of the domain. Now, if we didn't know the domain, the area of the domain, we would have to go ahead and do the double integral. But since we know the area of a triangle, we can just use that. And again, remember, this is going to be the area of a triangle is 1/2 times the base times the height, like this. And then that's going to be when that 3 looks like 27, if I'm doing this correctly. This will be 6 out of 9 is 54. Divided by 2 is 27. 27 square root of 14. Again, that gives us the area of this plane that's in the first octant, that area there. Again, and if you look at the projected area under the plane in the first octant, that's this part way down at the bottom here, which is redrawn over here. That's our domain. Again, take the derivatives, plug them in, and get that. Let's take a look at another example. Again, another example in rectangular coordinates. Find the surface area of the paraboloid z equal 50 minus 2x squared minus 2y squared. The area of this that lies above the xy plane. So let's take a look at that. So once again, we're in Cartesian or rectangular coordinates. We're going to use this equation over here. Now we already have it. Z is already a function of x and y, so that's already done. And the other thing we're going to have to do, we're going to have to see what the domain D over which we're integrating. And so we're going to plot this. And so we want to find where does the paraboloid intersect the xy plane? And of course, at the xy plane, that's where z is 0. So set z equal to 0 in this equation up here. So we'll have, let me rewrite this. So we'll have 0 equal 50 minus 2x squared minus 2y squared. Bring that all over to the left-hand side. So I'm going to bring it all over the left-hand side and divide everything by 2. So when we divide everything by 2, this will go down to 25, and these 2's will go away. We'll have x squared plus y squared is 25. Or, of course, x squared plus y squared is 5 squared. So that's going to be our domain. So basically, you're going to have a paraboloid like coming down sort of like this. It starts up here at 50. Like this. And it's going to intersect the xy plane when z is 0. In this domain down here, that's going to be this circle at the bottom here, which is going to be a circle of radius 5 in the xy plane. Like that. And so now we can go ahead and use the rest of our equations here. We need dz dx. So we're just going to go back up here and find dz dx. That's going to be minus 4x dz dy minus 4y, like this. And then the area, the surface area, will be the double integral. I won't write the equation down again, but remember, it'll be using this equation here. So we're going to have the square root of 1 plus minus 4x squared plus minus 4y squared dA, and over our domain, which is going to be that circle. And let's go ahead and multiply these out. So we're going to end up having the square root of 1, and this is going to be positive 16 plus another positive 16 times x squared, then times y squared. So we'll have 16s on both of these times x squared and y squared. Then I'm going to factor out the 16. And so we're integrating over a circle. So I'm going to go ahead and change the polar coordinates. And remember, when you change the polar, x squared plus y squared is r squared. Then always remember you have to put the Jacobian in when you convert the polar. So be sure to put that in and go from r equals 0 to r. We have a circle radius 5, theta 0, theta to 2 pi. And now right here, we'll do u substitution to do this. You can set u equal to what's inside here. And then you'll have du. I'll write the substitutions out here. U will be 1 plus 16r squared. Then when you do du, it'll be 32. So let me just put 32 over here times r dr, like that. Those are going to be your substitutions. And so you're going to replace this with u and put under square root. So you'll have u to the 1/2. Getting a little ahead of myself. And then integrate this. Excuse me, I left the 32 off here. Integrate this. This will give you u 3/2, 32 3/2 d theta. And this will cancel. That'll be 3 times 16 with 1 over 48. Like this. And then let's put our u back in here. And that will be 1 plus 16r squared to the 3/2. And then r went from 0 to 5 d theta. And when you put the bounds in, when you put the upper bound, this is going to be 5 squared plus 1. So that's going to end up being, so 5 squared times 16 is 400. Plus 1 is 401. So this would be like 401 to the 3 halves minus 1, because you put 0 in here, you still have a 1 here, 1 to the 3 halves, which is just 1. And you'll end up having, then we have to integrate once more for the theta. You'll end up having 1 over 48, 401 to the 3 halves, minus 1. Then when you have you have theta here, then put your upper bound and lower bound in. That'll be theta, and that'll be 2 pi. And that will be our answer. So again, just like before, we always have to find what the integration domain is. And in this case, we wanted the surface area above the XY plane. And in the XY plane, that's going to be covering this circle. That's why the circle is our domain. Of course, we found that by finding where this intersected. Then used our usual formula and got our answer. So we're going to now look at the surface area of a parametric surface. So consider this problem right here. Suppose we have a parametric surface which is given this way, and we want to find the surface area over this parameter. Of course, u and v are parameters. And so let's take a look at this. So once again, when we're doing this, we're using the parametric equation now. We're using this equation here to find the area, the surface area, where r is given parametrically in the parameters u and v. And so we're given x to be uv, y to be 2u plus v, z 2u minus v. And again, for our equation, we're going to need the derivative of this with respect to u. So let me do that. Derivative of this with respect to u is going to be v in here. And of course, this will be 2u plus 2v. So derivative of this one is going to be 2. Same thing over here. Now the derivative of this with respect to v will be, over here we'll have u, and we'll have 2, and we'll have negative 2, like this. So again, all I did was take the derivative of those with respect to u and v. Now, let's find the RU cross RV. Remember, that's what we need for our equation. It'd be I JK V22 U2 minus 2. And it would be I. This times this is minus 4 minus 4 again. Then negative J. And this will be minus 2V. And then minus 2 times U. Then finally over here, we're going to get plus K. 2V minus 2U, like that. And let me rewrite that a little bit better. So this is going to be negative 8I. And then we factor out the negative here. Those all become positive. So we'll have plus 2. Let me put the U first. Like this. J. And over here, we're going to have 2V minus 2UK, like that. And so, and let me actually just rate this a little bit better. This would be, let me factor out this 2 here, U plus V, then over here, 2V minus U, like that. And again, we want to find the the magnitude of U cross V. That'll be the square root of the sum of the squares. Like this. And let's see if we can simplify this. Of course, will be 64. And then over here, this will be 2 squared, which is 4. And then this is U V. Let me square that. That'll end up being U squared plus 2UV plus V squared. This is 4. That'll be V squared minus 2UV plus U squared. And one thing's nice is that notice we have a 4 times 2UV and then 4 minus 2UV. So these are going to cancel. That and that'll cancel. And so we'll end up having 64. And also then notice here as well, we'll have 4u squared and 4u squared. So we can put that together. That'll be 8u squared. And then we have 4v squared plus 4v squared will be 8v squared. Like this. And if you wanted to simplify it further, you could, I guess we could factor a 4 out of all these. And that would end up being, so we take a 4 out of here and a 4 out of here. So it'd be, and then take the square root of that. That'll end up giving us 16 plus 2u squared plus v squared. Again, all I did there was factor out a 4. I took the 4 out of here and here, left us with 2. And then I took a 4 out of here, which would leave us with 16. Pulled that out. Then I took the square root of the 4, gave us 2. So now we're ready to put this into our equation. And let me remind us of our equation for area. Our area is this double integral of RU cross RV dA. And that'll be this value here. That's going to be 2 square root of 16 plus 2u squared plus v squared. And now notice our domain was a circle of radius 3. And this, of course, due to the nature of the problem we have here, we'll change the polar. We're integrating over a circle. So let's change to polar. So we're going to have 2, and then we're going to call u squared plus v squared r squared, and we change the polar. 16 plus 2 r squared. Then always remember, put your Jacobian, r dr d theta. And a circle of radius 3, r equals 0, r equals 3, theta 0, theta 2 pi. And now here we can use u substitution. Du derivative here is 4r dr. So du over 4 is r dr. Those will end up being our substitutions. U the 1/2. We're replacing r dr with this. To this point, right here, so have the d theta. So I made the substitutions. Now we'll integrate this. And notice we have 2 over 4. That's just going to be a half. Let me put this half in front here. And integrate this. This would be 3 halves over 3 halves. d theta. And notice the 2's will cancel. This ends up being 1/3. And let me put our substitutions back in here. So I canceled those. I got 1/3. And we're going to have, this will be 16 plus 2r squared to the 3/2. Evaluated r equals 0, r equals 3. Those were going to be our bounds. And then theta is from 0 to 2 pi. I put our upper bound in, which is 16 plus 2, 3 squared, 3/2, minus our lower bound, 16, minus 2 times 0, which is 0. And so we have something like this, d theta. And then this is going to be, what is that? 2 times 9, which is 18. And so that'll be 18 plus 16 is 34 to the 3/2, minus 16 to the 3/2. Then we integrate with respect to theta. Theta will go from 0 to 2 pi. So we'll end up with 34 to the 3/2 minus 16 to the 3/2 times 2 pi. Like that. Again, that's how you handle it when you have a parametric surface given these parameters. You're basically given your domain of what you want to integrate, find your RU or V, do the cross product, and then find the magnitude of that, put it into your area equation, and use your domain, circle radius 3. In this case, we had to use U substitution to solve this. And we got our answer. And you could use your calculator if you wanted to find the final number for this.